Hello, good morning, everyone, and welcome to our SoCalGas RD&D research webinar. My name is Alan Lung, and I am the Customer End-Use Applications Technology Development Project Manager on the SoCalGas Research Development and Demonstration, or RD&D team. For today's webinar, we will be welcoming Dr. Jack Brower and Dr. Luca Mastropasqua from the University of California, Irvine to discuss their Department of Energy-sponsored research on decarbonizing steel production with green hydrogen. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all attendees. Please enter any questions in the question box. We'll review these during the Q&A session after the presentation. During the Q&A session, we will also open up the discussion for verbal questions. If you'd like to speak, click the raise hand icon to be called on during the Q&A session. When you are called on to ask a question, we will first grant you access to unmute, then you must manually unmute yourself. After asking your question, please go back on mute. Finally, you will find a few valuable documents in the handout box, including today's presentation. Now, a comment on SoCalGas's commitment to diversity. SoCalGas is dedicated to improving the quality of life in diverse communities we serve. To support this commitment, SoCalGas RD&D staff conduct outreach efforts and activities to engage with disadvantaged and underrepresented groups throughout California, notify researchers, entrepreneurs, and businesses about the RD&D program funding opportunities, share the results from the RD&D project to inform and educate the general public. Today's webinar is just one of the many ways that we do that. Track and report progress in diversity outreach efforts in our annual report. The SoCalGas RD&D program is divided into 5 areas that span the entire energy supply chain. From the low carbon resources where they look at renewable gas production, carbon capture, utilization and sequestration, to gas operations focused on the technology development of the operation side of the gas supply chain, to ultimately where we use the gaseous fuel from clean transportation, clean generation, and customer end-use applications. In 2020, the SoCalGas RD&D team managed 386 active research projects. On average, RD&D projects generated a 6.9 funding ratio, meaning for every $1 of RD&D funding provided to a project, the project also receives nearly $7 of external co-funding. For example, already in 2021, 5 RD&D projects have been awarded about $15 million from the California Energy Commission and the Department of Energy. More details on the RD&D program are available in the 2020 annual report, which is included in your handout today. This year, we produced a Spanish version of the annual report as well, to better communicate with the diverse communities in our service territory, also included in the handouts. Finally, we want to stay connected with you, our stakeholders in the research community and the general public. Please visit our webpage where you can find our annual report, news about the RD&D program, and recordings of our webinars, including this one today. Please reach out to the RD&D team via email with questions, comments, or research suggestions. We also maintain an RD&D page on the LinkedIn and CEC's research networking platform, Empower Innovation. Now, without further ado, I want to welcome Dr. Jack Brower and Dr. Luca Mastropasqua from the University of California, Irvine. Dr. Jack Brower is a professor of mechanical and aerospace engineering, and he is also the director of the Advanced Power and Energy Program, or APEP, at UC Irvine. Dr. Brower is an expert in high-temperature electrochemical systems dynamics for complementing and converting renewable energy with a PhD from MIT and bachelor's and master's degrees from UC Irvine. Co-leading the effort with Dr. Jack Brower is Dr. Luca Mastropasqua, a senior scientist at APEP, and who has a PhD, master's, and bachelor's degree from the Politecnico di Milano. Jack and Luca, I'm excited to hear about the story behind your research and the technology you're working on with the decarbonization of steel production with green hydrogen. I will now hand over the presentation mode to you, Jack, so you can provide us the details. Thank you.
Thank you very much, Alan. It is our pleasure to be here today and to share with you some exciting research that we are beginning at the University of California, Irvine, and with partners that you can see on the screen here as I go into presentation mode. Hopefully you can all see this now. Thank you so much for this opportunity to speak to you today about a very exciting effort that we are conducting here today. This is an effort to decarbonize and lower emissions associated with steel production. The title of our effort is Solid Oxide Electrolysis Cells Integrated with Direct Reduced Iron Plants for Producing Green Steel. We have an awesome team that is leading this effort, including us at the Advanced Power and Energy Program, and our partners, Fuel Cell Energy. Fuel Cell Energy is a leading manufacturer of solid oxide systems. Hatch, a major steel organization. LEAP and Politecnico di Milano, two Italian organizations that are outstanding when it comes to thermodynamics and integration of steel and electrolysis technologies. And SoCalGas, a partner in this effort from the very beginning. We also are very grateful for the support of the US Department of Energy. My pointer seems to not be working, so I'm going to use the arrow instead. We're thankful for the support of the US Department of Energy, which is providing the majority of the funding for this effort. We're also grateful to our board of advisors, and you can see them up here in the right-hand corner of the slide. Nucor, ArcelorMittal, Tenova, and recently added Midrex. So we have steel companies that are the most famous from all around the world that are also participating in our advisory board. We have a website for this project, which you can see on the screen here at the APEP Hydrogen Green Steel. That's what H2GS stands for, Hydrogen Green Steel. You can also use this code here. You can scan it either from the slides or from this screen right now to actually get access to this website from this QR code. So the project goal and milestones are to first advance, demonstrate, and optimize a thermally and chemically integrated solid oxide electrolysis cell system as a co-producer of hydrogen and oxygen with a direct reduced iron plant at 1 ton per week of product scale. That's the overall project goal. And we have milestones and subsets of goals that you can see down here. We intend to reduce specific primary energy consumption to less than 8 gigajoules per ton of DRI product. We also expect to have electric to hydrogen efficiency for the SOEC stack of less than 35 kilowatt hours per kilogram of hydrogen produced. This is a very low number, and it's achieved because of the integrated process that we propose. And we will reduce the specific CO2 emissions rate to less than 90 kilograms of CO2 per ton of DRI product. This is about a 20 times reduction in specific CO2 emissions. And we will pilot a system at a production capacity of 1 ton per week at TRL 4. So this is pretty low TRL stuff. This stands for technology readiness level, which goes all the way up to 9 for commercial technology. We will then build a design for scaling up the plant to 2 million tons per year of DRI product capacity. And finally, we want the total capital specific cost to be less than $200 per ton equivalent pig iron per year. This is what we proposed to the US DOE with our partners, including SoCalGas, and it's what we hope to deliver. And this would be very impactful because we know that from the perspective of direct industrial CO2 emissions, iron and steel production comprise almost 1/3 of all of these emissions. 28% come from iron and steel. As a matter of fact, 6 to 6.5% of the total anthropogenic CO2 emissions in society come from the steel industry. And if you look at the traditional way in which you actually manufacture steel using a blast furnace plus basic oxygen furnace, that's what this BF plus BOF stands for, compared to what we propose, the two hydrogen routes, the hydrogen direct reduction and the hybrid hydrogen direct reduction, you can see that we have very much different performance characteristics. Those performance characteristics include a halving, roughly, of the energy intensity from 19 to 22 gigajoules per ton to less than 8 or less than 9 gigajoules per ton. And then this 20 times reduction from 1.8 to 2.1 tons of CO2 per ton of crude steel, all the way down to less than 0.1. The specific cost is a little bit reduced from what we can do today. And the electric load, which is not necessary in the traditional means, is going to be less than 7 gigajoules electricity per ton of crude steel. In one sense, this is electrifying the means of producing steel through the hydrogen vector. And as you can see in the bottom here, we have a certain amount of kilowatt hours per kilogram that we expect to achieve with a reference solid oxide cell. But notice with the integration in HDR, we can actually lower that from 40 to 35 because of some thermal integration with the DRI furnace. And notice that it's the hybrid HDR that actually can do synthesis gas, syngas. Solid oxide electrolysis cells can electrolyze both CO2 and water. And this is how we would integrate that technology. So, what are we doing in this particular project? We know that we have a lot of emissions, around 7% of the global anthropogenic emissions of CO2 that are due to the steel industry. And there is expected to be more steel, not less steel, manufactured in the future. As a matter of fact, 20% increase in steel production is projected to 2040. And this is primarily as we see countries increasingly industrializing and improving their quality of life, their economic status. And we've talked about these numbers before, the energy intensity that we hope to drop, but there's a couple of ways that you could possibly decarbonize the iron and steel industry. And that's what I'm showing on this particular chart. We can see that the traditional way of making steel using a blast furnace plus basic oxygen furnace could be complemented by carbon capture and storage. To simply take the carbon that is emitted from this process and to capture it and then sequester it. We, on the other hand, are proposing an alternative way of making steel. Instead of making it through blast furnace plus basic oxygen furnace, We would like to make it through this direct reduced iron process. Now, there are a couple of other projects internationally. One that we note here in Sweden, that's called Hybrid. They are investing $51.8 million to integrate a proton exchange membrane electrolysis system with direct reduced iron to advance another method for alternative steelmaking routes. We also have a project from ArcelorMittal in Hamburg, Germany, where they're demonstrating a novel DRI plant. And then there's a ThyssenKrupp Steel grant that was recently awarded in 2019 that is also similar to the kinds of things we are doing. Ours is novel, though, from all of these, because we are integrating this kind of direct reduced iron plant that I'm showing here with solid oxide electrolysis. So what happens with direct reduced iron? That's basically shown here, where we have entering the top of the furnace the iron ore. Okay, the iron ore. These are the compounds that are oxidized iron. They comprise things like hematite, magnetite, and wustite that must be reduced to produce the iron Fe as they go down the length of this furnace. And this flows from top to bottom of a direct reduced iron furnace by having the reducing gas flow from bottom to top in this DRI furnace. So we have a counterflow of the reducing gas that increasingly reacts with the iron ore to reduce the hematite to magnetite to wustite and finally to iron. And we can see some of the chemical reactions that must take place in this furnace on the left-hand side, where we have reduction that can occur with hydrogen. And you see many of these iron ore products reacting with hydrogen to produce further reduced iron or even iron itself. Or it can be reduced by reaction with carbon monoxide. So both of these gases, hydrogen and carbon monoxide, can reduce the iron. There also could be a reduction of CO2 plus carbon to form two COs, which can subsequently react with the iron. Now, two things are important in the final product that the DRI process makes. One of them is metallization, because we want to get at least between 90 and 96% pure iron. Okay, that is one of the key things that must be produced at the bottom of this DRI furnace. We also would like to introduce a bit of carbon into that DRI product, which is necessary for some of the downstream products. And that amount of carbon should be between 0.3 and 0.8%. So this is the DRI process. It's different than the blast furnace basic oxygen furnace and has this counterflow reduction process. And what we're going to do is we're going to integrate it with a high temperature solid oxide electrolysis cell steam and CO2 electrolysis system. As a matter of fact, here you can see the polarization curves for a solid oxide electrolysis cell. These are polarization curves that we determined and use in our models, but also that compare well with the experimental capabilities of the solid oxide electrolysis cells that fuel cell energy can produce. And you can see, depending upon the temperature at which we operate these cells, they will have less or more polarization. So we can go to higher current densities if we are at higher temperatures. And notice here what happens if we're doing steam electrolysis. We have the steam plus electrons producing the hydrogen and oxygen ions. The oxygen ions are transmitted through the electrolyte to form oxygen on the alternate electrode, the anode. by consuming 2 electrons to make oxygen. So we have an oxygen-rich stream that comes out this side and a hydrogen-rich stream that comes out this side. So we co-produce oxygen in this case. Now, solid oxide electrolysis is interesting and different from proton exchange membrane electrolysis in many respects. And one of the key respects is that we can operate solid oxide electrolysis systems at a thermoneutral point. This is a point at which the losses associated with the electrochemistry exactly overcome the endothermicity of the electrolysis reactions, so that the heat balance is perfect. If we go to higher current densities, then we produce a little bit of excess heat. If we go to lower current densities, we require a little bit of heat. And this is where it becomes really interesting to integrate solid oxide electrolysis with something that can produce heat and give the heat to the system. And this is what we can do with the DRI furnace. We can then operate in this endothermic region at lower current density and lower voltage with a little bit of heat to accomplish the thermal balance, so that the overall efficiency goes up, electrical efficiency goes up. Now, the maximum endothermic point is right here, where you can see the peak of endothermicity, and then we have thermoneutral here. Okay, and of course, the electrical efficiency is what is improved if we can operate in these endothermic conditions and use heat instead of electricity to make the hydrogen. All right, now the state-of-the-art solid oxide cell could be integrated. State-of-the-art in DRI is to use natural gas. Okay, this is in contrast to what we are suggesting, where we are going to use a solid oxide cell that has renewable electricity and renewable heat as an input, okay, to co-produce hydrogen and oxygen. So instead of using natural gas in the traditional DRI plant, we are using hydrogen to do the reduction of the iron, making green steel because there's no carbon that comes out then from the process, but also having oxygen that can be used in other parts of the plant and for other end uses. So with that, I want to turn it over to Luca to present. Luca?
Yes. Can you hear me?
Yes.
Do you want me to?
Yeah, please share your screen.
Okay.
We saw it for a second there.
Can you see it now?
Yes, looks good.
Okay. All right, so I'll continue here. So how are we going to do this? This is the first schematic or layout configuration that we proposed when we proposed this idea to DOE. So this is somewhat more complete, but still simplified schematic of the idea. So on the right-hand side of this drawing, you have the shaft furnace, where we saw earlier, you have the at the top of the furnace, you have the iron ore coming at the top. And at the bottom of the shaft furnace, you have the reducing gas which comes in counterflow configuration with the iron ore. And at the very bottom, we have the final product, the DRI. So the integration aspect is that we already produce a top gas from the shaft furnace that is, if we imagine the reducing gas being composed mainly of hydrogen, the top gas will be constituted mainly of some unreacted hydrogen, but mainly steam. So because this top gas is already at high temperature and already characterized by a high content of steam, the integration aspect is really to recycle back this top gas after some heat recovery and preheating to reach the temperatures of the SOEC stack to feed it back directly into the cathode compartment of the SOEC, which will electrochemically reduce the steam content in the top gas, and therefore produce a hydrogen-rich stream at the outlet. At the same time, the oxygen that is going to be stripped out from the steam is going to be collected on the anode side across the electrochemical membrane, and so we will also produce a pure stream of oxygen at the very outlet of the anode compartment of the SOEC. So the reducing gas will be mainly constituted by hydrogen, and we will then be able to recycle it back after some heat recovery and preheating into the shaft furnace. In this specific configuration, the preheating is done by using some natural gas, which, however, in order to avoid additional CO2 emissions, for this preheating, is going to be oxidized using the oxygen coming out from the anode compartment. So the combustion that we use in this case for preheating of the reducing gas is an oxy-fuel combustion, and so we will be able to capture most of the CO2 coming from this oxidation. So the reducing gas is then be able to be recycled back into the shaft furnace at high temperature to restart the loop. So as you can see, there is a hydrogen loop or steam loop between the shaft furnace and the SOEC, and so the cell really operates as an oxygen pump or oxygen removal device that will remove the oxygen from the steam, and then the oxygen will be put back into the loop by the iron ore up here. So as Jack mentioned earlier, the advantage of having this integration is that the SOEC can exploit the enthalpic content of the top gas to reduce the electrochemical energy input from renewable energy sources by displacing that with some thermal input. So as I mentioned, we will expecting to not have any CO2 emissions apart from the small CO2 that is going to be used, or natural gas that is going to be used to preheat the reducing gas. So in order to understand how the SOEC operates in these particular conditions, which are definitely not conventional for compared to sort of simple hydrogen production, we are modeling these systems both in terms of system integration and the SOEC specific module. So at UCI, we have this dimensional model that allows us to understand what happens inside the SOEC when we operate the cell in the particular conditions for the integration with the DRI. So what we do is to discretize the channel of the SOEC into many small pieces to understand how the hydrogen production occurs in a dimensional fashion. So this, for example, are preliminary results of our dimensional model, where you can see on the left-hand side the profile of current density along the length of the channel, meaning, and just as a note, note that this y-axis is a negative, so we have an increase in current density up to a sort of 60% of the channel, and then the current density will decrease towards the outlet of the channel. And we have designed this cell to operate at around 0.9 amps per square centimeter on average. So despite, so on average, this cell will produce 0.9 amps per square centimeter, but the dimensional variation is as reported here. And this chart on the right shows the concept that Jack was describing earlier, where we have the losses, the electrochemical losses, thermal power produced by the electrochemical losses, which in this case are lower compared to the sorry, the other way around. The endothermic generation from the electrochemical reduction of steam is lower compared to the thermal power of the electrochemical losses. So this particular configuration shows an exothermic operation of the SOEC. And you can see that from the cell voltage, which is slightly higher than the thermoneutral voltage that Jack explained earlier. We have, in this particular configuration, a steam utilization of 85%, meaning that we are converting 85% of the inlet steam into hydrogen. And that means, from a system perspective, that a certain amount of oxygen is also produced, and the steam utilization of the SOEC will be correlated to the conversion of iron ore in the shaft furnace, because the oxygen balance has to close as well. And then finally, you can see here from a stack perspective, the efficiency for hydrogen and oxygen generation, which for this particular configuration sort of meets the expectations that we had in one of the first slides. So we can produce hydrogen at less than 35 kilowatt-hour per kilogram of hydrogen, and we can produce oxygen, pure oxygen, at less than 4.5 kilowatt-hour per kilogram. So from a system perspective, we have some, and from an operational perspective also, we have trade-offs that we need to overcome to design the system. So say that we want to produce the same amount of hydrogen from the SOEC stack, we could increase the current density, which is the current divided by the active area of the SOEC. So if we want to increase the current density at a constant current, means that we could reduce the active area. So meaning producing the same amount of hydrogen with fewer number of cells. And this is advantageous because, as you can see down here, the area is related to the capex of the SOEC. And therefore, if we reduce the capex, we reduce the specific cost of hydrogen production. However, if we increase the current density, because of the polarization curves that we showed earlier, we will also have an increase in electric power input. And this will reduce the first law efficiency of the conversion. So there is a trade-off between efficiency and cost that is is going to be explored during this project. In terms of preliminary thermodynamic performance of the system, of the integrated system, as mentioned earlier, we are planning on targeting 0.85% of carburization in the final DRI product, and greater than 96%, in this case 97.5% of metallization in the final product. And the preliminary analysis that we have conducted show that the primary energy consumption of the HDR case, meaning the renewable energy electric input plus the natural gas that it's needed for the preheating and to supply the carbon to the final product, ranges between 7.4 and 8.3 gigajoule per ton of the final DRI product considered hot. And in terms of CO2 emissions, the range associated to the consumption of primary energy is between 40 and 60 kilograms of CO2 per ton of DRI. So this preliminary thermodynamic results are in line with our expectations, and we are exploring different configurations to integrate the heat recovery, integrate the or minimize the natural gas consumption. So more is gonna come in terms of system integration in the future. And now I would like to just mention the possibility that Jack touched upon earlier of the fact that SOEC can operate in coelectrolysis mode. So this is the same picture that we showed earlier, with the difference that on the cathode side, we can feed not just steam, but also CO2. So CO2 can be electrochemically converted into the cathode of the SOEC to produce CO. So at the outlet of the cathode, we would then have a renewable syngas comprised mainly of hydrogen and CO. So this is also quite interesting. As you can see on the right-hand side of the screen, if we increase the temperature for, if you look at on the very right-hand side here, the coelectrolysis reaction becomes it's advantageous to operate it at high temperature for the same reason that we discussed earlier for steam, as we can reduce the amount of electricity input at the advantage of increasing the amount of heat input. So the fact that we can electrochemically reduce CO2 allows us to include some carbon into that loop between the DRI furnace and the SOEC. So the schematic becomes from the schematic that we showed earlier. The difference is that we can inject some natural gas into the loop between the SOEC and the DRI. This natural gas is then used mainly to supply carbon atoms to the in this loop, and therefore use that natural gas to provide carbon to the final DRI product. So this configuration really allows to regulate the carbon content of the DRI product without increasing natural gas makeup, because we have a recycle of the carbon between the DRI furnace and the SOEC. And the novel aspect, not only in terms of system integration, as you can see here, is that we will, in the project, demonstrate coelectrolysis for application in configuration with the DRI system. So how are we going to demonstrate this? As of now, we are planning on demonstrating, so reaching TRL 4, technology readiness level of 4, using a so-called hardware-in-the-loop configuration, where we will have real hardware of the SOEC system. So on the left-hand side, you can see we will have a SOEC system deployed in the lab of Fuel Cell Energy in Danbury, Connecticut. And it's going to be a containerized solution that is going to be connected, well, it's going to be measured with all sorts of physical sensors, and we will provide electric input and then all the operating conditions that are required based on our system simulation. The hardware is then is going to communicate with a DRI simulator that is going to actuate sensors to supply the top gas, the resulting top gas from the DRI, hydrogen DRI kinetics to the SOEC. So the loop is going to be using this hardware in the loop configuration where the DRI is going to be simulated with a real-time model that is going to talk to back to the SOEC stack. And this is the final demonstration of the project that is going to take place towards the end of the third year of our effort. Just a couple of words on the demonstration system itself. Fuel Cell Energy, which is our partner that is going to develop the SOEC module, is based in Danbury, Connecticut, and they already have pressurized stacks. This is one example of the stacks that we're going to use. And this stack is going to be placed inside a pressure vessels that is going to able to operate up to 8.6 bar. And the pressure vessels is going to reproduce the exact conditions that we are going to simulate with the thermal integration with the DRI system. As you can see, the final SOEC module is going to be containerized in such a configuration, and so we hope that as a follow-up to the project, this system can be deployed or shipped into an industrial site to demonstrate this concept in a real industrial application. In terms of follow-up or future work, the project is divided into 5 technical work packages, and we've mainly talked in this presentation about the first 2. So the first work package is really the system integration and thermodynamic analysis, of which LEAP, our Italian partner, is responsible for. LEAP and Politecnico di Milano are primarily responsible for this work package. The second work package is the design of the SOEC module, which we are, UCI, is primarily responsible for, and I've shown you some of the results that we've obtained. The third work package is Fuel Cell Energy responsibility, mainly because it's the testing and design of the prototype and the construction of the demonstration unit. And the fourth work package is really where we put everything together in terms of demonstration of the pilot scale system. So the fourth work package is where we're going to build the hardware in the loop demonstration, and so couple the hardware SOEC module with the real-time DRI simulator. And the fifth work package is Hatch is going to be primarily responsible for this, which is the scale up of the demonstration unit to a commercially relevant scale to meet the economic targets of the project. This is just a summary of all of our collaborators and primarily responsibilities. And so we wanted to point out that we are working actively with industrial advisors to the project. So we are meeting with them regularly in order to sort of not to lose focus of what's really important for the industry. So in summary, I just want to conclude that as of now, we have been able to demonstrate with modeling activities that we can reduce the primary energy consumption of steel making by more than 65. Oh, I've lost. Can you still see my?
Keep going.
I cannot see my screen anymore.
Well, I can continue then and say that we have been able to show that we can thermally integrate these, chemically integrate these, and achieve really substantial goals, like a 20 times reduction in CO2 and a substantial reduction, almost halving, of the primary energy consumption. We also are showing that we can, oh, now you stopped sharing? Sorry. Okay. And we're also showing that both hydrogen and renewable syngas fuels can be integrated in this way if you use solid oxide electrolysis cells. And there's no one else in the world that is doing anything like this except for us and our team to decarbonize and reduce primary energy consumption, making green steel using solid oxide electrolysis cells and systems. So we thank you for the opportunity to present this to you and welcome your questions.
Yes, and also I would like to acknowledge all of our partners and names of people that are contributing to the project over here.
Thank you very much. Yes, acknowledgements. Whole bunch of really talented people that we're working with, and it's a wonderful team. Okay,
thanks for the presentation, Jack and Luca. I apologize. I think I might have cut off Luca when I turned on my webcam, so that probably interrupted his presentation. But I'm so sorry for that. I threw you off your flow. But now I'd like to spend 10 to 15 minutes for our Q&A. And quick reminder for our Q&A: if you have a question, please feel free to raise your hand. There's a click the raise hand icon, which will allow us to identify you, to give you the ability to unmute, so that you can ask your questions. So when you ask your questions afterwards, please manually unmute, and then when you ask your questions, please mute. And if you have any questions in writing, please feel free to use the question box, and we will ask the question for you. So I have been monitoring the question box, and I do see a few questions kind of rolling in, and I will help ask the questions for them. So the first question that I received from Ken Grishabar, sorry for butchering the last name. First question is, what level of dust can the solid oxide electrolysis cell handle? And his second question is, what is the minimum temperature it can operate at? And then his third question is, what pressure does it operate at? So loaded question.
Yeah, we have three questions there. Let me make a brief attempt, if you don't mind. So SOECs, it's interesting that you noted dust, because absolutely, when you operate a DRI furnace, when you manufacture steel in general, there is usually a lot of dust involved, and an SOEC can't handle hardly any dust. We have to completely remove that dust from the top gas. And there are means by which it can be done. As a matter of fact, it's currently done at natural gas fired DRI plants by cooling the gas and using filtering technology. We're looking at a number of different options for removing the dust from that top gas, which include things like cyclones and filters, high temperature filters, and the like to do that. Secondly, you asked about the minimum temperature that the SOEC can operate at. The SOECs can go down to something like 700 C if you use traditional SOEC technology. If you use novel material sets, you can get down to maybe 550 C, but typically you're talking about 700 to 850 or so as a typical operating range for SOECs. And then finally, what pressure does it operate at? Well, this is one of the novel aspects of what we're going to be proving in this effort, going up to 8 atmospheres, 8 bar. Most SOECs that are being developed today are operating at atmospheric pressure. We're going to put this inside of a pressure vessel and operate it at 8 bars so that it can actually operate the same pressure range as the DRI furnace itself. Okay, so this is part of the integration process that we are investigating. Luca, do you want to add anything to that?
No, I agree that the dust issue is definitely one that is going to be we will need to spend a lot of time to find the good solution that can be implemented in a real industrial application. So we are aware that that's a challenge, and we need to sort of find solutions that can either remove dust at high temperature, so therefore without losing too much of the thermal integration, or either partially or totally cool down some of the top gas to remove the dust.
And we know that we can do that. That's the traditional means by which dust is removed. But we would like to keep the thermal integration as best as possible, and so we're looking at alternative routes for that.
Very interesting question. Thank you for your question, Ken. I hope that response was a good response to your question. And I received another question from a Scott Jorgensen, and his question is, why does the system use natural gas to heat the reducing mixture rather than using the heat inherently in the molten iron, either directly or via a heat transfer fluid?
That's an interesting idea. You should know that the reactions with pure hydrogen are a net endothermic in the DRI furnace, unless we add a little bit of carbon and integrating something thermally without it being the gas itself, top gas that's recycled, and goes back into the bottom of the furnace after it is reduced. That's a difficult thing to do, to integrate thermally the steel with the preheating that occurs there. So it's an interesting idea to try and use heat from the DRI furnace directly. But again, we have to put heat into the system overall anyway, okay? And so this is part of the reason why we actually are doing that natural gas combustion. We could possibly have some additional hydrogen production that we would siphon off of the SOEC. That could be an alternate way too, but then we'd have to burn it in the oxygen because we need to get that heat into the system. I think that answers that question.
Great, and I see that there's a raised hand, so I'll give Mark Allendorf an opportunity to ask his question via voice chat. Mark, I'll unmute you, so please feel free to unmute so you can ask your question.
Can you hear me?
Yes.
Great. Thank you for the nice presentation. I've got two questions. Will this process be perfectly in balance from a mass flow point of view? In other words, will the consumption of hydrogen in the DRI exactly equal what is produced out of the SOEC? And if not, are you going to store hydrogen on site, and how would you do that? That's question one. And the question two is, you are emitting some CO2, so how are you planning to trap that? Are you going to use something like ethanolamine, the conventional way, which requires some power? So how does that affect the economics of your process?
You want to go ahead, Luca?
Yeah. So for the first question, there are some configurations that, so we are of course having a range of scenarios and a range of configurations that we are exploring. So some of these configurations have a perfectly balanced hydrogen production and consumption. So we are not net producers of hydrogen. But as far as the original configurations that we first thought of, that is a net exporter of hydrogen and oxygen, which we need to. That's another sort of output of this configuration. If we aren't in fact exporters of hydrogen, at that point we need to so for now we are planning on not storing hydrogen on site, but just using that as a sort of renewable product that we can sell, possibly to decarbonize other steel making processes like blending, selling that hydrogen to a blast furnace or other industrial processes down the line. And the same applies for oxygen. So oxygen is going to be another renewable product that can be sold to maybe a basic oxygen furnace down the line. The second question related to the CO2 emissions is we are not using any absorption system for carbon capture because we are combusting the natural gas using pure oxygen. So we will not have any sort of nitrogen diluents in the final exhaust line. So we will just need to condensate the steam or the water.
Cool the gas to remove the water.
So we just need to recover
a little bit of energy too, though.
So we will need to do some heat recovery definitely on the exhaust line. The preliminary thermodynamic integration system integration that we've done show that we can compensate most of the steam, recovering the heat, and that heat can also be used to produce additional power with a bottoming cycle that can be an ORC or something like that can produce power with the recovered heat. So as of now, we're not including any absorption CO2 capture system.
Thank you.
Yep.
Thank you for your questions. I also see a Steve Alameda raising his hand. Steve, I'll go ahead and unmute you so you can ask your question.
Thanks so much, Alan. Great to see both Dr. Brower and Dr. Mastro-Pasqua. Good to see you both. My question is this: with regards to your earlier statement, Jack, you had shared that manufacturing is projected to rise and extend, and understanding that, the financing necessary for this new infrastructure in which this would be a piece of. Luca had shared that while not a true net exporter, but my question does come on, could the industrial customer be a producer of hydrogen in which it could optimize the investment tax credit associated with production and or storage, which are two new variables for investment tax credits to promote widespread hydrogen development?
Yeah, very nice. Thank you, Steve. It's nice to hear your voice. Absolutely, it is possible that not only could we export and sell oxygen to other entities that might use it, we could also overproduce hydrogen and have it integrated with other end uses, some that are perhaps even more valuable than using it for steel production, like using it in transportation and getting some kind of credit for integrating the hydrogen production with other end uses. So yes, introducing this as a hydrogen ecosystem or hydrogen producing net and having some income from other streams might be attractive. Again, that will depend upon the location that you are doing it, what incentives are available in that location, what alternate uses might be adjacent to that. But interesting idea. Thank you for the question.
Thank you.
Thank you. Jack, I have another question from Alan Dassault. His question is, why not be agnostic on the source of hydrogen as long as it is zero carbon emission? For example, methane with sequestered carbon may provide a cost-competitive alternative to hydrogen from wind or solar.
Yeah, that's a very interesting question. It's also very prescient because there's a lot of debate going on right now about the use of methane and natural gas, especially fossil natural gas, which has emissions of methane along the value chain. But I agree with the sentiment here and believe that all ways in which we can reduce carbon and criteria pollutant emissions must be explored, and we should adopt those which are most cost effective at actually reducing carbon emissions. Okay, and use of methane plus carbon sequestration, I believe, will be required for a portion of our decarbonization goals. I want to suggest, though, that the use of primary sun and wind power and electrolysis is likely to comprise a larger fraction of the decarbonization in the end, okay, compared to the carbon sequestration technologies. It's for a couple of reasons that I make that suggestion. The first is that fossil energy is finite, and we will not be able to use it perpetually unless we slow down very much. Secondly, solar and wind power are quite ubiquitous. They are available almost everywhere around the world in varying quantities. And as a result, I see the sustainable energy future having more sun and wind power than it does sequestered methane. Again, I'm not saying anything bad against the sequestered methane idea. This is a good idea, okay? I just don't think it's going to be as ubiquitous.
Thanks, Jack. Another question from Mark Daniels. His question is, when do you expect the product will be available for implementation on scale?
Good question. DRI technology that uses natural gas is already available at commercial scale, and some of our advisory team is already implementing such, which is also already a very big improvement compared to the basic oxygen furnace and blast furnace. Okay, so that DRI technology is available. The solid oxide electrolysis cell technology integrated with that DRI plant is quite novel. Like I'm saying, at the end of our project, we're only going to get to TRL4. So it's because it's very, very novel idea from my perspective, that thermal integration and chemical integration. So I would suspect that it would take perhaps another 5 years or so after our project is done, 2.5 years from now, for it to become commercially available. Don't know if that's a good timeline or not, but it's what I suspect, something like that.
Great. Gordon Gudarzi, I see your hand is raised for quite some time. I'll go ahead and unmute you so you can ask your question. Gordon, are you still there? Okay, yeah, I think he's away from his keyboard. But I do see another question from Ken Grishaber, and I'll go ahead and unmute you.
Hello, thank you, and thank you for answering my earlier questions. As you were questions came to my mind. Number one is, when you convert the DRI plant to 100% hydrogen, I'm going from memory and it's very fuzzy, but is that going to affect the type of iron ore that you can use?
I'm not sure how to answer that question. We should probably have our Hatch colleagues who are steel experts. I'm not a steel expert, neither is Luca. We're both solid oxide electrolysis cell experts. But in our discussions with both the advisory team.
Okay, all right. And
in our discussions with both the advisory team.
Okay, can you hear me?
Yeah, but there's a huge delay, I'm sorry.
Okay, yeah, good. Well, I didn't know if it was only my end. The other question pertained, as you were speaking and people were talking about the size of this, what would the footprint of this plant be roughly, and how largely can you scale it up to a single, say, module or plant?
It can be scaled up to the full-scale steel plants of today, the modern plants of today. It's already being used at that scale, again, like I said, with the methane-based DRI.
Okay.
Mm-hmm.
Right.
And that scale is roughly 2 million tons per year DRI product, 2 million tons per day DRI product. Is that correct?
No, it'd be per year, but I meant the size of the SOEF. That could one unit, one train of SOEC rather could handle that, or would it be multiple trains?
It's very, okay, so all electrolysis technology is modular. As a matter of fact, the individual cells are going to be very small, and they're going to be integrated into stacks, which are also very small in comparison to the overall system. So yes, it's going to be modular.
Thank you.
Yeah, thank you for that question. So Alan, I see a question from Vito Pinto.
Yeah, go ahead and take it. I'll go ahead and read it for us though.
Yes,
What
please.
is the final hydrogen quality that you would expect as output of the pilot plant? What is the expected lifetime of the solid oxide cell module? Could the lifetime of the solid oxide cell be affected somehow by this way of operation? If so, how? Up to which scale this integration would be competitive?
So first of all, Vito, I wish I could see you. We miss you here, and congratulations on all the important work you're doing there in Europe. Vito was a visiting student scholar here at APEP for a while ago. Okay, the final hydrogen quality doesn't have to be pure for this integration to work well. That's the first point. And notice that we start with a stream that's roughly 50% steam, 50% hydrogen, and we convert about 80 to 85% of the steam back to hydrogen in the recycle, okay? So we are not making pure hydrogen. We're just reducing a very large amount of the water to hydrogen and recirculating the whole stream. Okay, so that's kind of how we are doing that in the pilot plant. The expected lifetime of the SOEC module, I would suggest that at least 5 years is required, and that's mostly what the manufacturers are trying to get to SOEC modules that would last for 5 years. In this particular application, it might even be more challenging to do so because of the tough environment of removing all the dust and everything. But I would guess that's 5 years. If you can get it down to 5 years, typically then you have these major overhauls that occur every 5 years, which is pretty typical in industrial processes, and that would work out fairly well and provide for reasonable economics. I would suggest that we're not quite there yet with a 5-year lifetime, by the way, for SOEC technology. And yes, this way of operation, I think, will be a little more challenging than the typical operation on pure steam. That's not coming from a hot top gas that's mixed with water and mixed with hydrogen and could have some contaminants in it. Okay, and then you had one last question, last part of the question. I don't know if I've answered it.
Yeah, so Ken asked a follow-on question is, what is the sulfur tolerance of the solid oxide cell? There could be a sulfur pickup in the mid-rex plant.
Oh, you guys know how to touch on the worst, I mean, the most difficult challenges that we have in this, right? Yes, the dust is a very big challenge, but so is sulfur, absolutely. And sulfur is not easily managed in any traditional fuel cell. But there are some novel electrocatalysts that we could put into the cathode of these SOECs that are quite sulfur tolerant. So there is some exploration of that we are doing on the side. It's not really a part of this particular effort. We are not funded to study sulfur tolerance in this particular effort, but we are aware of that as being a challenge. And so, yeah.
Also, I would like
to,
I would just like to comment on that, that the sulfur in the top gas, as far as I know, is mainly related to, I mean, it can definitely be sulfur coming from the iron ore, but the majority of it, as far as I know, comes from the natural gas. So if we don't have that
plants in current DRI plants, absolutely, yeah, but there still will be some, and we probably, yeah.
Great, and I see that we have a question, a hand raised from Fabio Miani. I'll go ahead and unmute you, Fabio, so you can ask your question. Fabio, are you there? I've unmuted you. Go ahead and unmute yourself so you can ask your question.
I'm there, yes, I'm there, Alan. So thank you, Luca and Jack, for your very nice presentation. Yeah, I was figuring out some 10 months ago some of idea, because there is a large possibility to have funds to go in industrial process for green steel in Europe for the current moment. So I think that for DRI point, the big trouble is going not too big, because going too big, it may cause some troubles, because you have then the economy. So which is the idea? Going to an industrial scale of the dimension of the yearly production, if you would go in that direction in the future, of course. So normally DRI plant, the smaller ones are around 250,000 tons a year. This is the basic minimum typical industrial plant for that. But I do believe that it would be something smaller, because it takes time, it takes investment, it takes risk, and it takes also money to produce some green steel, a little bit more than the standard steel. So thank you for allowing me the asking you questions. Thank you for your presentations.
That's a very nice question, and absolutely, there would be very likely no investment in this before it got tested at a pilot scale first. And interestingly, there are several pilot DRI plants available at much smaller than the full industrial scale of 200, 250 million tons per year. So that's likely the path. The path would be that it would first be tested at a full pilot scale. So you have a pilot scale DRI with pilot scale SOEC, and then the investment in the 200 million tons per year plant would come later.
Okay, thank you so much.
Yeah, thank you.
Thank you for your question. And I see that Cynthia Carter has raised her hand as well. I'll go ahead and unmute Cynthia.
Hi, thank you for getting my question. Quick question. I'm hearing, the introduction of hydrogen and combustion equipment is creating a higher NOx level. Is there any concern about that for this type of equipment?
So notice in this kind of equipment, this is not combustion. This is reducing iron ore. And notice also that the top gas is recirculated. Okay, so we're not emitting that stream in the first place. So this is a very different process from the ones that you have heard about, maybe even in the news lately, in which hydrogen would be burned, perhaps in mixtures with natural gas, in power plants, or other industrial burners, things like that, or even in appliances for that matter.
That's good.
Now we happen to in a different set of projects, studied these kinds of phenomenon too. And my colleague, Professor Vince McDonnell, has studied this kind of phenomena, natural gas hydrogen mixtures and pure hydrogen combustion over many, many years, a couple of decades, as a matter of fact. And yes, hydrogen can burn hotter than other fuels, and as a result could lead to nitrogen oxide emissions increases. And under some circumstances, it absolutely does that. In the broad set of appliances and industrial burners that my colleague, Professor McDonnell, investigated, he found that in most cases, adding hydrogen to natural gas actually, without modifying the burners, okay, actually reduces emissions, and it's for a surprising result, for a surprising reason. Even though it might burn hotter, it also has a faster flame speed, and as a result, the flame attaches itself closer to the burner tip, exchanges more heat with that burner tip, and actually cools the overall combustion process, leading to lower nitrogen oxides. Now, that doesn't always happen with all burner types, but most of the burners he investigated show this reduction. So while people might expect hydrogen in mixtures with natural gas to actually increase emissions, we've found, for the most part, it actually reduces emissions. This is a separate topic, though. It's not associated with steel making.
Thank you very much.
You're welcome.
Thank you for your question, Cynthia. And I do see Rapak Das has raised his hand as well. So I'll go ahead and unmute Rapak, and Rapak, please ask your question.
Dr. Brewer and Luca, thanks so much for the excellent presentation. Can you hear me properly?
Yes.
Yes, I've got a small question, like what is the trade-off between the thermal neutrality and the efficiency inside the system? Because we all know that when you go for the thermoneutral point, the electrical efficiency gets reduced, I think, right?
Well,
so what's the
yes.
trade-off?
Yeah. So we possibly could show the screen slide. Are we showing slides here?
Yes, I see the slide being presented.
So Luca, if you go to that slide where we show the thermoneutrality and endothermicity, that might be nice. So you're correct to identify the fact that if we operate under exothermic conditions, then we're producing more heat than we need, and we'll have lower efficiency. So if you look at this exothermic regime to the right of this curve here, to the right of this curve, then we are going to have lower efficiency. And when we get to thermoneutral, that would improve the efficiency. However, on the opposite side, where it is endothermic, continuing to reduce the current, okay, and adding some heat to the process improves the electrical efficiency. So as we go to lower and lower current densities, we can improve efficiency, but you have to start adding heat once you get close to the thermoneutral point. Okay, so that's the trade-off. If we have heat available, yes, let's use it, and let's get close to thermoneutral or even below thermoneutral. That's the trade-off.
Great explanation, and the presentation is excellent. Thank you so much, Dr. Brower and Luca, for the fantastic time with us.
You're welcome. Thank you for your question.
Thank you. So I see that there's no further question, and we are just at about time. So I'd actually like to thank the presenters for their exciting presentation today on the hydrogen. And thank you all for asking very interesting and engaging questions. We look forward to the results of this research. And just a quick reminder, this webinar is being recorded and it will be available on the SoCalGas Research and Development webpage. Thank you all for attendance today, and take care. Goodbye.
Thank you. Thank you.